What if the biggest clue that our picture of reality is wrong came from a thought experiment that Einstein wrote with two colleagues at the Institute for Advanced Study in 1935? He wasn't trying to prove quantum mechanics was right. He was trying to show it was incomplete, that two particles couldn't possibly stay connected across a room, let alone a galaxy. He wrote that paper to win the argument. Instead, the math he used to make his case turned out to be the exact blueprint future scientists needed to run the experiments that proved him wrong about the nature of reality itself. Einstein, Podolsky, and Rosen published their paper in 1935, fully expecting it to close a debate. They weren't attacking quantum mechanics outright. They were arguing it was incomplete, that it left out some deeper layer of information that would explain the strange connections the theory seemed to describe between distant particles. Einstein was actually irritated when the New York Times ran a story headlined "Einstein Attacks Quantum Theory," because he felt scientific disputes belonged in scientific journals, not newspapers. He was also privately frustrated that the paper felt smothered by formalism, since Podolsky had written most of it, and the result didn't quite say what Einstein wanted it to say. The specific problem they pointed to went like this. Say you create two particles together so their properties are linked, then send them in opposite directions. When you measure one of them, you instantly know something about the other one, no matter how far apart they are. Einstein said that gives you only two options. Either some signal traveled between the particles faster than light, which he knew couldn't happen, or the second particle already carried that property the whole time, and quantum mechanics just wasn't keeping track of it. He called that second option hidden variables, the idea that there's a deeper reality underneath the quantum description that the theory wasn't capturing. The phrase he used for the alternative, where measuring one particle actually affects another one instantly across space, was spooky action at a distance. He meant it as a dig. It was his way of saying the theory was broken, because any respectable theory of physics shouldn't need to invoke invisible instant connections between objects. Niels Bohr fired back almost right away, and his answer was philosophically sharp, even if it didn't fully satisfy Einstein. Bohr's position, which sat at the center of what's called the Copenhagen interpretation, was that choosing to measure one property of a particle excludes the possibility of measuring the other. So asking what a particle really is before you measure it is the wrong question entirely. Quantum mechanics isn't leaving something out, Bohr argued. Predetermined values for both position and momentum aren't just unknown, they're invalid, because the measurement itself is what forces a property into existence. Einstein never bought it. He spent the rest of his career treating quantum mechanics the way you'd treat a weather forecast. Useful, often accurate, but clearly not the full picture. A good map of a city gets you where you need to go, but it doesn't show you the buildings, and Einstein felt quantum mechanics was exactly like that, a practical tool sitting on top of a reality it couldn't fully describe. What neither side could do was test any of this. The whole argument in 1935 existed entirely in the space of logic and philosophy, because nobody had the equipment or even the framework to run a real experiment on the question yet. So it just sat there, frozen, for close to 3 decades. Most physicists moved on to other problems because the Einstein-Bohr dispute looked like exactly the kind of thing you can debate forever without resolving. Then, a physicist named John Bell read the EPR paper and spotted something nobody else had noticed. Einstein's argument wasn't just a philosophical position. Underneath all the logic, it was a mathematical claim about how strong the correlations between distant particles could ever be if hidden variables were real. Bell's 1964 paper showed that local hidden variable theories, the kind Einstein preferred, actually couldn't reproduce the correlations quantum mechanics predicted. And a mathematical claim, unlike a philosophical one, can be checked with an experiment. Bell's theorem did something nobody had managed in 30 years of arguing. It turned a philosophy problem into a physics problem. If Einstein's picture of reality was right, if particles carry their properties before you measure them, and nothing connects distant objects without a signal traveling between them, then the correlations you'd measure between entangled particles could only ever reach a certain strength. Bell calculated exactly what that ceiling was and wrote it up as an inequality. You run the experiment, you read the number, and the number tells you who's right. Most physicists in the 1960s looked at this and shrugged. The equipment to run the test barely existed, and a lot of people assumed quantum mechanics would win anyway. So why spend years building the apparatus just to confirm what everyone already expected? Richard Feynman was reportedly highly offended by the whole idea, claiming quantum mechanics was so obviously correct, it didn't even need testing. The project felt more like philosophy dressed up in math than something worth putting on a lab bench. John Clauser didn't see it that way. He read Bell's paper as a graduate student and immediately wanted to build the test, partly because the question genuinely gripped him, and partly because, according to his own account, he wasn't sure quantum mechanics would win. He actually expected Einstein might be right, and he built his apparatus from leftover scrap, salvaged from his physics department, to do it. His faculty told him that chasing quantum foundations would wreck his career, that it wasn't real physics, that he was wasting his time. He pushed ahead anyway, and eventually ran the experiment with a colleague in the early 1970s. The setup used pairs of photons created together, so their polarizations were linked. Clauser measured the correlations between the two photons as they traveled in opposite directions, and compared that number to Bell's ceiling. The result came back at 6.3 sigma above what local realism allowed, which in physics is the gold standard for certainty, not a tiny sliver you could explain away. Clauser had bet on Einstein and lost, and when he mailed his results to the physicist, Yakir Aharonov, who'd taken the other side of the bet, he enclosed a $2 bill. There were still loopholes in that original experiment, ways a skeptic could argue the setup hadn't fully closed off every escape route for hidden variables. Maybe the detectors weren't efficient enough, or the measurements weren't truly independent of each other. Later experiments in the 1980s addressed those gaps by switching the measurement settings while the photons were already in flight, so there was no way for one side to influence the other. The results held. Then, fully loophole-free tests in 2015 closed the remaining technical objections, and the answer didn't change. Every single time, the correlations came out above Bell's ceiling. Not sometimes, not usually, every time. What that means is worth sitting with for a second. Einstein's argument wasn't just a guess. It was a logically tight framework for what reality has to look like if objects carry fixed properties and connections between distant things require a signal. The universe doesn't match it. In 2022, Clauser received the Nobel Prize in Physics, alongside Alain Aspect and Anton Zeilinger, for the experiments his faculty once called a waste of time. So entanglement isn't a theoretical quirk or a loophole that future experiments might close. It's a confirmed property of the universe, and that immediately raises a different question. What exactly is it, and what does it actually let you do? Two particles are entangled when their quantum states are linked in a way that neither particle's individual properties can explain on their own. The clearest way to see this uses photon polarization. You create two photons together in a process where their polarizations have to come out opposite, but neither photon has a fixed status until the moment of measurement. Both of them sit in a superposition, meaning both possibilities exist at once until something forces a result. When you measure your photon and it comes out vertically polarized, the other photon instantly locks into horizontal polarization, no matter where it is. It doesn't matter if that second photon is across the lab or across the galaxy, the result is immediate. And this isn't because the two photons secretly agreed on their polarizations before they parted ways, because Bell's experiments already ruled that out. It happens because the two photons share a single quantum state, and measuring one half of that state settles the whole thing at once. That probably sounds like faster than light communication, and almost every explanation of entanglement accidentally makes it sound that way. You measured one particle, the other one responded instantly, so information traveled, right? It didn't, and the reason connects to something called the no cloning theorem. When you measure your photon, you get a random result. Vertical or horizontal, you don't get to pick, and you can't predict which one you'll get. The person on the far end of the galaxy measures their photon and also gets a random result. Because neither of you can copy the random data you're receiving to compare it in real time, there's no way to extract a message from it. The correlation between your results only becomes visible when you compare your two lists over a normal channel, one that's limited by the speed of light like everything else. So entanglement is a correlation that's too strong to have any classical explanation, but because you can't control which random result you get, you can't encode anything into it. In a real lab, scientists create entangled photon pairs through a process called spontaneous parametric down conversion, where a laser passes through a specially cut crystal and occasionally converts one photon into two lower energy photons that share a quantum state. You can also entangle ions, individual atoms, and the superconducting circuits that sit at the heart of quantum computers. So this isn't limited to photons. In 2017, China's Messias satellite used exactly this approach to distribute entangled photon pairs between ground stations more than 1,200 kilometers apart, verifying the correlations using the same CHSH inequality that came directly out of Bell's theorem. The entangled state itself is fragile in a way that makes it genuinely hard to work with. A single stray photon bumping into your system, a tiny vibration, a small temperature change, any of these can break the correlation through a process called decoherence, where the two particles that stop sharing a quantum state and just become two separate particles with ordinary classical properties. Keeping entanglement alive long enough to actually use it is one of the hardest engineering problems in quantum technology right now. What entanglement can do is act as a resource for things that are otherwise impossible, including quantum key distribution, where security isn't based on a math problem that might eventually be cracked, but on a physical law that can't be. Any attempt to intercept the entangled particles disturbs the quantum state in a way that's directly detectable. But entanglement isn't the only place where quantum mechanics breaks what classical physics says should be possible. Tunneling is the other place where quantum mechanics rewrites what you'd expect. In classical physics, if a ball rolling toward a hill doesn't have enough energy to reach the top, it stops and rolls back. The hill is a hard limit. Quantum mechanics says that rule doesn't apply to subatomic particles. A particle approaching a barrier it shouldn't be able to cross still has a real probability of showing up on the other side, and the total probability of finding that particle somewhere stays at 1, meaning it's certain to exist somewhere. What shifts is where it can be, because part of its probability wave leaks through the barrier instead of bouncing back entirely. This is quantum tunneling, and it comes directly from what particles actually are at the quantum scale. A particle isn't a tiny ball sitting at a precise location. It's a probability wave spread out through space, and when that wave runs into a barrier, most of it bounces back, but a small portion leaks through. If the barrier is thin enough, that leaking portion is big enough to produce a measurable effect. The particle doesn't go around the barrier or find a weak spot in it. Inside the barrier, its wave decays exponentially as it goes deeper, so a thicker barrier means less tunneling. But less isn't zero, and that distinction turns out to matter enormously. Take the sun. Protons in the sun's core don't carry enough thermal energy to push through their mutual electromagnetic repulsion and actually touch each other. Classically, fusion shouldn't happen, and the sun should be cold and dark. Protons tunnel through that repulsive barrier with a small probability, and because the sun's core contains an almost unimaginable number of protons colliding constantly, Those small probabilities stack up into the energy output that keeps the planet warm. Radioactive decay works the same way. An alpha particle sits inside a nucleus, held in by the strong nuclear force. And classically, it doesn't have enough energy to escape. It tunnels through the barrier anyway, and when it does, that's what we call alpha decay. The rate of decay for a given radioactive element ties directly to how probable that tunneling event is, which depends on the thickness and height of the barrier the alpha particle faces. In labs, engineers use tunneling deliberately to image surfaces at the atomic scale in devices called scanning tunneling microscopes. A metal tip gets brought to within about a nanometer of a surface, and electrons tunnel across that gap. The current that flows depends so sensitively on the exact distance that moving the tip by even a fraction of a nanometer changes the current by a measurable amount. And that sensitivity is what lets the microscope map individual atoms. Inside your phone, though, tunneling is a problem. Transistors have shrunk so small that insulating layers thinner than about 1 nanometer can't actually block electron flow anymore, because electrons tunnel straight through them. That leakage wastes power and generates heat, and it's one of the hard physical limits on how small a transistor can get. Engineers designing the next generation of chips aren't fighting a manufacturing challenge at that point. They're fighting a law of quantum mechanics. Both entanglement and tunneling come back to the same thing. Particles aren't little balls with fixed positions. They're probability waves, and the sun burning overhead and the heat coming off your phone are both direct evidence of that. Einstein wrote the EPR paper to prove quantum mechanics was broken, and instead, it handed scientists the exact test that proved local realism isn't how our universe works. That's not a small thing. Two particles can share a state that no distance breaks, and a particle can cross a barrier it has no classical right to cross. And both of those things are happening right now, in the sun, in your phone, and in quantum communication systems that check for eavesdroppers by measuring Bell inequality violations directly. The paper Einstein wrote to kill quantum mechanics now sits at the foundation of the US National Quantum Initiative and global quantum network research. The next part of this series gets into the actual math, where the wave function stops being a picture and becomes something you can calculate with